Okay, so you know the Fourier transform from 1D signals. So let's make a way of what this is. So let's say that you have here a pulse like this. So you have a square signal like this. And then what this Fourier transform is saying is that you can approximate this signal as much as you like by adding signs. And these sinusoidal waves, you have to control a few things. You have to control the amplitude, you have to control the phase and the frequency. So let's go. Okay, so let's say that we have a sinusoidal wave. One. And then we have, for example, let's say I y t is a sine on some frequency plus some phase. And the frequency there are multiple ways of writing, so this is the same as this one. And it's the same as this one. Okay, so let's put units to things. So let's say that this doesn't have any unit. So y doesn't have any unit. So what about a? Does it have units or not? So a should have the same units as y. So if y doesn't have units, a doesn't have units either. Okay, so let's look at this one. So the whole thing has to be radians, okay? Because this is the argument of the sign. So the whole thing is radians. This is seconds. So this has to be radian per second. And this has to be radians. And then what about this one? This one is put in the radians. So this is 1/2. And what about this one? Is the unit of lambda. Seconds. So this is called period of wavelength. This one, 1/2 is the same as hertz. And this is frequency, this is frequency. These two are frequency variables. This lambda is a period or it is a wavelength. And what else here? Yeah, so when you are adding these sinusoids, you have to control. You can control three things. One is the amplitude. The other one is frequency or the wavelength or whatever. So they are all equivalent. And the other one is the phase. So by controlling these things, so you have time. You have to choose what is the amplitude, what is the wavelength, so what is the distance between one maximum and the next. This is the wavelength. And what is the phase? So the phase moves the sign to the left or to the right with the same frequency. Okay, so and by adding many of these signs, you can approximate any signal as much as you like. There are problems at the discontinuities. So when the signal, the input signal is discontinuous, there will be these marks here that how are they called? The Gibbs effect. Okay, so this is the Gibbs effect. And that's it. So here we have this. So we have the amplitude, we have the wavelength, that is this one, frequency, and phase is 0 in this case. And we have a sum. So a sum, what does it mean having a sum there? What are we assuming by having a sum? That the input signal is periodic. Okay, so you have a few things here. I'm sure you have heard of all of them. So you have the Fourier series, and the Fourier transform. And the Fourier series is what periodic signals. And the Fourier transform is called aperiodic and periodic signals. So you can treat both. And this is one thing. And you have also to make some distinctions. So one is about periodicity. And then you also have another classification according to the kind of signals. So call it the nature of signals. We have seen two natures. So we have seen continuous signals. Continuous. T. And you have also seen discrete signals. Like X of n. So depending on what is the combination that you use, you have the discrete Fourier series, the discrete Fourier transform, the continuous Fourier series, continuous Fourier transform. And sometimes we will illustrate things with continuous Fourier transform that is simpler to show. But the same concepts apply to all the combinations. Okay, so here is a continuous Fourier series. Okay, so it is a series. We have an infinite sum. And it is a continuous because the argument is t. Okay, but the idea is that any signal, discrete or continuous, you can approximate as a sum of sinusoids. Okay, so yeah, let's look at this. This was a sinusoid. So what we had here was a single sinusoid. But what we have is that in general, any signal, anyone, or we call it now X, any signal is a sum. Let's give it to Fourier series for the moment. So it is a sum. And for the moment, we don't put limits to that. Of some amplitudes and then some sinusoid, given frequencies. Okay, so here are the three components. And this is called coefficient. Fourier coefficient. And these ones here is the Fourier basis. Here is an important word, that is basis. Okay, so when we talk about the basis, what we know well is how to represent vectors. of a vector. So we have E1, E2, E3. And we have a point here. This point, you say this point is exact number 7, 3, 1. Okay, so what does it mean? It means that this is 7 times E1 plus 3 times 2 plus 1 times 3. And how did I come to this 7, 3, and 1? Okay, so first, just to make it similar to this one, I can rewrite this thing this way. So I can rewrite this as the sum over some indexes of some amplitudes that are the 7, 3, and 1 times my basis. You see? So this is the coefficients. So this is my basis. How did I compute the coefficients? So if and only if my basis is orthogonal, then the AI is the inner product between your vector, call it R, and my basis. So I can substitute that there, and this is the sum of my vector so let's see what that is. So let's look at this one. So this is 7 according to that coding. And that 7 is the length, is the projection of this thing. So this point here is 7, and then E1. So you have to travel 7 units in the direction of E1. Okay, so this is the length. This part here is the length. Of the projection of R onto Okay, so we will do the same with the Fourier transform. So these will be lengths. So this is my basis. I have to project my signal onto my basis. I have to compute these coefficients. And those coefficients will be the length of the projection of x of t onto the basis. Okay. That will come later. But what we see is that they have this spirit. This is an amplitude, and this is my basis. Okay, so this is just to show how we can approximate more and more the input signal. So let's say that we have only one sign, two signs, both sides. So we are stopping this addition. We are going from -1 to 1, from -2 to 2, from -3 to 3. So from one sign, two signs, four signs. Okay, so the more signs we add, the closer we are to the square function, except for these discontinuities. The discontinuity is the Fourier transform class problem. this is the same I have explained. So you can express that when you control a sine, you have to control the amplitude, you have to control the phase shift, that is whether you move it to the left or to the right, and you have to control the period or the frequency, that is what is the distance between equivalent points. So these 2 points here, these 2 points are equivalent. These 2 points are equivalent. So say that something is a period. So let's go back to this one. That was pure sine. That this applies to any wave, okay? For the sine too, but in general for any wave. So for any wave, what you have is that if I take this and I add my period, I have the same value as a t. Okay, so you take a time point t, you evaluate y at that time point, and then you evaluate y at t plus lambda, and you get the same one for any t. This is valid for all t. Okay, so this is the wave. And then you have 1 over lambda is measured in hertz, 2 pi over lambda is measured in radians, in seconds. All this we define already. Okay, so it seems that these lengths are important. For computing the length, we need an inner product. So how do I define an inner product between 2 functions? Okay, so let's say that I have a couple of functions. I have function ft. I have the function g of t. So this is whatever, this is another function, whichever that is. They can be complex values, okay, so they can take complex numbers. And I have to compute the length of the projection of this onto this one. And we will define that in this way. So it will be the integral from minus infinity to infinity of f of t multiplied by the complex conjugate of t differential. Okay, so you have to multiply the two point by point. Well, the g you have to complex conjugate, then you multiply, and then you integrate from minus infinity to infinity. That will be our definition of. This will be our definition of inner product. Okay, that is what is in the slide. There is a difference. He's going from minus lambda divided by 2 to lambda divided by 2. This is only for value for periodic signal. So if your signal is periodic, then you define it in this way. If your signal is not, define it in this way. And yeah, so we have automatically we have an extension of some concept. So let's look at this. E1 is perpendicular to E2. This was our ortho. Orthonormal has 2 parts. The first one is ortho, and the second one is normal. So ortho means perpendicular. Normal means having unit, all the EIs have unit length. Okay, so orthogonality. So we know that E1 is orthogonal to E2, so we can write it this way. Here I'm saying E1 E1 is orthogonal to E2. Okay, so the angle between the two is 90 degrees. And this implies that E1 is equal to 0. And then this is that the length of E1, the length of E2 times the cosine of the angle between E1 and E2 is 0. Okay, so this is unique. This is 1, this is 1, this is 1, and then this one has to be 0. And then the cosine of an angle is 0. So that means that the angle is 90 degrees. That is why E1 and E2, they form an angle of 90 degrees. That is something that we have not defined yet. That is the norm of it. So how do we define norms? So we define norms as the square root of the inner product of the vector with itself. Of a vector with itself. We haven't defined inner product formally for vectors of this type, but you know it already. So if you have use some other letters, so if you have a couple of vectors u and v, this is u transpose. Okay. So now we have everything consistent for R3. So we have defined an inner product. Then we have, based on the inner product, we have defined how to measure lengths. And then we understand that if two vectors, the inner product is 0, is because the angle between the two is also is 90 degrees. And the same concepts apply here. So let's say that you have a couple of functions. You have a couple of functions such that the inner product between these two is 0. So that means that f of t is orthogonal. So we have extended the concept of orthogonality now to functions. So now we can define when two functions are orthogonal. And one of the properties that we will require later is this one. The bases have to be orthonormal. Okay, good. So this is it. So f and g, they have an inner product of 0 when f and g doesn't have anything in common. Okay, so let's see how you can compute these things. So let's say that you have a function f, you have a function g, like this here. So we have g, and then you have the inner product of f times g. So you have point by point f times g, so this is f of t times g of t. And now we are only showing f times g. And now you have to compute the integral. So the integral is all this area. Whatever that number is the inner product. The area is always the inner product. And then, if the area is 0, then they are perpendicular. And if the area is not 0, they are not perpendicular. So this area is not 0. You see that the positive areas are larger than the negative areas. This one, you have function f, the same as the one before. Now you have a different age. So before it was g, now it is 8. And now the area this area is. Okay, so and then we have our Fourier transform. I think the one that is, I will not comment all of them. You have similar derivations in previous courses about signals. So I will concentrate on this one, that I think it is the simplest one. Okay, so which is my basis for the Fourier transform? So, which is my basis for the Fourier transform? So I have to define some functions. I call those functions phi of t. That will be the complex exponentials. So this will be my orthonormal basis. So these are the complex functions. So for every I, you have a different frequency. That is what you are changing with the I. And then you can compute, you have a signal. So let's say that I have a signal. X of t. I can compute the inner product between phi, each one of these phi's, and my signal. So this length that we have discussed just now. And then I have to sum overall my elements in my basis. So this has the same structure as we had before with vectors. So let's rewrite the one with vectors in it. So for a vector, it was the sum of the length of that vector projected the unit basis times the unit basis. That's the same structure. So this thing is this, and then you have this part, and then you are summing over all the elements on your basis. And this was the Fourier series. This is series because it is a sum. This is my Fourier series. So my Fourier series is nothing more than expressing a vector, a signal, in a different basis. Okay, so now you may wonder, okay, so when I have my signal, drawn in this fashion, this. So when I have my signal expressed in this way, x of t, then my signal is this one. This signal, the Fourier space, it is expressed like this, but in the real space, there must be another series, another basis that allows me to express this thing. So I can think of this signal as a collection of samples. I will separate them, but they're infinitely close to each other. And then my signal is made of these Dirac deltas. Okay, so let's look at one of these. Let's call it, I will use the same notation I used later. So I will call it tau. So at this point, what I have is x of tau. So what I have is that x of t is a sum over all taus of x of tau, that is this height, minus my delta shift tau. So if I take all these deltas that are infinitely close to each other, and I put them one after the other, what I have is x of t. Okay, so now what is my basis? My basis is delta t minus tau for all tau. Okay, so this is my basis. And then this, what is this? This should be, this is my basis. Okay, so this is my basis. This is the sum. And this has to be the length. Actually, this one is the inner product between x of t and your basis at that point. Then remember, this is just by definition. This is the integral between x of t, x of t, delta t minus tau, t from minus infinity to infinity. This is my definition of inner product. And by definition of the delta, this is x of tau as it should. This should be this thing. Okay, so now what I know, my real space representation, this one, is a representation in which I'm using this basis. While the Fourier transform is a representation, is the representation of the same signal, where I'm using this basis. So depending on which is the basis I'm using, I have the real space representation or I have the Fourier space representation. All I have done is just to change the basis. Good. Yes, sir. So here we have this is the Fourier series, so we are going from minus lambda half to lambda half. And then we have f of t times my basis. So what my basis? Should I stay here? So my basis is the complex exponential. So inner product between f of t and my complex exponential is from, let's make it as in the slides, Fourier series. Then it is f of t, and then this one complex conjugate. The complex conjugate of this one is this thing. And then differential of t. So now you understand why we have a minus in the Fourier transform. Actually, this is the Fourier transform. This one is the Fourier transform of f evaluating r omega r. It is that inner, that length. And then when you reconstruct here, you have the basis. So here you have the minus because of the complex quantity. But here you don't have a minus. So in the forward Fourier transform, you have the negative complex exponential in the when you go back to real space, you don't have the positive complex exponential.
basis we are representing linear spaces of the
Well, what?
with the orthogonal basis.
With the orthonormal. Orthonormal means that the elements in the basis, they have unit, they are orthogonal to each other and they have unity length. And this applies to both. This one is orthonormal. So the Fourier space is orthonormal, but this one is also orthonormal. So real space is orthonormal. Fourier basis is also orthonormal. Okay, so all these are. This is going to detail onto the 1D Fourier series, but I don't think it is important. This you already know. When you define a complex exponential in this state. Okay. And in general, when you compute this, Fourier transform, this sum is complex. So these are complex numbers. You are multiplying complex numbers by real numbers, so that is complex again. And then you are summing many of them. So you are summing many complex numbers. So in general, they will be a complex number. So just to follow the notation of the slide, it will be something that depends on the frequency. So it depends on which is the frequency that you are adding. And it will have an amplitude and it will have a phase. When you have a complex number, you can represent it like this. So this is the phase of that complex number. And then you put it as a complex exponential. Okay, so you have amplitude. This is amplitude. And phase. So in general, this Fourier transform will be a complex number. And if it is a complex number, it will have amplitude and phase. And if you want, you can also say, you can also write this thing this way. That is this one. So you have Ci cosine of the angle of Ci plus A plus sine of the angle of Ci. So you have real part, and imaginary part. So you can do both representations, either as real and imaginary parts or amplitude and phase, and they are totally equivalent. So far, so good. This is somehow key. Okay. So you have real part, imaginary part, the amplitudes there. Okay, now the amplitude and phase. So, why are Fourier coefficients complex numbers? Now we already know. We are adding many complex numbers. These are complex numbers, and then we are multiplying by a real one. So this, in general, this is a complex number, and then we are adding many of those. Then it is a complex. So let's do that. So this is Fourier transform. So this is Fourier transform. We have defined so far. We have defined the continuous sequence. But we can do the same with complex valued signals. So we can do the same with discrete signals, sorry. So we can do the same with discrete, so you can say, okay, so I will have x of n, and x of n, I can compute basis, the basis was 5, okay, I, and then this is 1, n. So I have to define my basis. My basis will be this, d minus j by I, n. Okay. And I such that I go from 0 to n. This will be my complex value basis. And this is assuming that my signal is discrete and goes from 0 to n. So we have a signal that is discrete and it goes this is x of n, this is n. Then there are two distinct points. One is here 0, this is n minus 1. So we have in total n samples. And then our frequencies, we also need n frequencies. So here we also have n coefficients. So we will have one coefficient for each one of these complex values, complex exponentials, and we have n of them. So if your input signal has n samples, your Fourier transform also has n samples. But now they are complex. Okay, so this is our these are our complex value signals. So this is the Fourier transform. So the Fourier transform will continue for continuous signals. So it has a continuous signal and then multiplied by this. And this is this inner product. And for discrete signals, this is your discrete signal. Then you multiply by this. This is your. There's this 1 over n. So this 1 over n is to make it orthonormal. So to make it. So we were assuming that these ones are orthonormal. So they have unit length. What happens if our things don't have unit length? So let's say that we have a basis. Let's do it with vectors, which is easier. So let's say that we have u1. So we have a basis that is u1, u2, u3. But they don't have unit. They are normal to each other, so they are orthogonal, but they are not. They don't have unit length. So you can substitute by u1 divided by the norm of u1, u2 by the length, u3 by the length, 3. And now they are normal, right? Okay, so now my expression of my vectors here would be my expressions of my vectors. So I have R. R is the sum over I of R times my unit vectors. So the unit vectors are these ones. U1, let's see, I. I. This one. Times my unit vector. My unit vector is I. this is number, so they can go out of the expression. This will be so this part is the same that we had before, but now we have this turning product. This is the 1 over n. 1 over n that we have in the discrete Fourier transform. The coefficients that we have in the Fourier transform, those coefficients in front, they come from the fact that these bases may not be normal. They may not have unit length. And then you have to multiply by something to make it unit length. This one over the length of those vector system. So, yeah. So the other thing is whether, so all this is talking about orthogonality. We have assumed, we will not prove it anyway. I have said that this basis is orthonormal. So if it is not normal, we can easily normalize it. So we simply divide by the length. And then there is another constraint that is the part of orthogonality. So the part of orthogonality says that if you take any one of these bases and you multiply by another one, then this will be 0. This will be 0 if I is different from j. It will be 0 if I is different from j. And then, because they are orthonormal, it will be 1 if I is equal to j. So this happens for the complex exponentials. It also happens for the deltas. So if you multiply two deltas, that they are not in the same location, the product is 0. If you multiply two deltas that are at the same location, the product is 1. And the same happens for the complex exponential. So if you multiply two waves that have different frequencies, remind in the Fourier transform, this part refers to the frequency. This is frequency. Okay, so if you multiply two waves of different frequencies, the product is 0. If you multiply two waves of the same frequency, the product is 1. So if you want this one, if you want it to be unit length, you have to divide by the square root of it. And now they are unit length. Otherwise, they have a length that is different from 1.
This part, because of the calculation of that function,
So this way? Yeah. So if you take any elements of your basis function, and these are your elements in the basis function, you take any one, if you have, how many do we have? We have n of them. So you take two that are different. You compute what is the length of the projection of one onto the other, is 0, if the frequencies are different. If you have two waves of different frequencies, this product is 0. So there is no intersection between them. And if if you take two waves that are the same, so I and j is the same number, then the product is 1. But to be 1, you need this 1 over the square root of L. That we know where it is coming from. It is this norm here. Okay, 1 over the square root of L is this norm, just to make it unit. Okay, so good time to make a break, I think. Okay, somebody book this one. So you have the bases that are these complex exponentials. I'll take this one, this basis. So you have a basis. Then you have a signal. You multiply this one by every element in the basis. Instead of this, we call it omega. This one. So you multiply by every element in the basis. And then you have to use all the bases. Reconstruct. Now, because it is a continuous basis, okay? So we are representing the Fourier transform. So I should sum over all elements of my basis, but all the elements of my basis. My basis is indexed by omega. And then this will be my signal. Okay, so my signal I project onto each one of the elements of the basis, and then I use those elements. So this thing here, this thing here is the Fourier transform. So the Fourier transform of x of t evaluating at omega is this inner x of t multiplied by x. This is my Fourier transform. And this one and this one is the inverse one. This is the inverse Fourier transform. So in the inverse Fourier transform, these elements here are the Fourier coefficients. The Fourier coefficients are just these. So something important. Many times you make mistakes here. Is okay, so this is the integral of minus infinity to infinity of x t minus a omega t. Differential of now t or omega. Differential of t. So if you integrate this expression depends on omega and t. If you integrate in t, you only have left the dependence on omega. And that is why this one depends on omega. So the Fourier transform depends on omega, so that means that you are integrating in t. And here it is the opposite. This depends on omega. So let's call it this one here. Let's call it hat for the so for the Fourier transform. So it depends on omega. This one depends on omega and t, but then you are integrating in omega, so that at the end it depends on the t. So you have to be very careful on which variable you're integrating, whether you are in Fourier space or real space. And very often you mix the variables. This is a very serious mistake. So as an engineer, you cannot make this mistake of integrating in the wrong space, or mixing or constructing expressions that have the wrong variable. Okay, so here we have everything. So we have the Fourier transform, we have the inverse Fourier transform, and all we needed was to define a basis. Okay, so now all this was one dimension. So all this is just a reminder of everything you know. Let's go now 2 dimensions. So now we go 2 dimensions. So we have images. So let's go down. We have an image in real space. Now this plays the role of time. So the location plays the role of time. Now I have to define a basis. So I have to define a basis that depends on frequency. But now my frequency, in 1 dimension we have only 1 frequency. In 2 dimensions we have 2 frequencies. So now my frequency will be a vector. And will be a vector. And will be now I will write the 1 in one dimension so that you can see how similar they are. It is just the same. So it is the same. Only that before it was just the product because they were scalar values, and now they are vector values. So I will compute the inner product rather than the okay, so I can also write this thing. Let's write this thing. So this is, let's say that R is made of X and Y. So this is equal to X times Y times Y. It is the same if you want. You can also write it in this way. R transpose. That is the standard definition of the inner product of vectors. Any one of these expressions is equivalent. And this is the 1D. So this is 1D. And this is 2D. Or in general, 3D. You can make R and W to be of any dimension. Aquí. Una T. No. Porque esta T es la variable espacial o la variable temporal que te dice dónde estás en la señal. Aquí el que te hace de quién estás, dónde estás en la señal es la R. Yo te lo explico así, pero muestra lo mismo que exactamente igual. O sea que empezaba subiendo la R. Tienen la misma estructura, ¿no?
O sea, pero entonces el que tiene una dimensión también sería como dos dimensiones omega.
No, este tendría una sola dimensión. De hecho, si mis vectores, o sea, si yo defino vectores de una dimensión, esto también. Any other question? No? Okay, so now I have my basis, and then everything that we have done before now applies. So this is our Fourier transform. So I have to multiply my input image now by every one of the elements of my basis. And now my basis has 2 frequency components rather than 1. And then when I'm going back, I have to take my Fourier transform that now depends on 2 dimensions. And I have to multiply by every one of the elements in the basis, and I have to sum over all my bases. So let's see that. So this expression. So this is one dimension. This is now. How do I define the two-dimensional frequencies? So now, for him it is u and v, x and y. So u and v are the frequency vectors, and x and y the real space vectors. If it is the discrete signal, then we can also write the frequency vectors in this way. Yeah. Okay, so let's do it here. So if my image has, let's say, R rows and C columns. So this one, the last one is R minus 1, the last one is C minus 1, it's a C, it's a C. So it has R rows and C columns. So now my frequency is, my basis, I have to write also in a way that, so I will write it this way, say omega R, and now my such that omega is of this form, is 2 pi divided by the number of, we are in x, we have to define, so this is x, this is y. So in x we have c columns, and this is omega x. This one will be omega x. Omega x. So it will be this one divided by c times I, and then the other one 2 pi divided by r times c, and I goes from 0 to c minus 1, j goes from 0 to r minus 1. Then I close this. And this is omega 1. So now if your input is discrete, so if your input is discrete, it would be better notation to use brackets, square brackets. So if your input is discrete, then your basis is also discrete. So you don't have infinitely many frequencies. So you have a discrete set of frequencies. This discrete set is defined in the same way as we did before. So before we said 2 pi divided by n times I. It's the same, but now we have to be careful that there are two n's, different number of samples in each direction. So it is the same. So this is the basis for continuous images. This is the basis for discrete images. Here you see M and N. I have used R and C, but I think they are not clear. And then you define the Fourier transform and the inverse Fourier transform in the same way. So this is the Fourier transform. So it is the inner product between your basis and your image. This is the inner product between your basis and your image. And then the inverse Fourier transform is here. So you take these coefficients and you multiply by your basis and you integrate over your basis, or you sum over your basis. I think my notation is a little bit more clear. Okay, so this is another visual representation of the things. So let's say that you have an image. Then you can compute the Fourier transform. These are the frequency components. And then this Fourier transform, you use it as the coefficients to recover the original image. said there, as a comment, that is the following. I will do it in 1D because for me it is simple to draw. So let's say that we have this x of t, okay, and I will do it. My x of t is this one. So it goes from 0 to t. But what you are assuming is that from outside it is 0. So x of t outside the interval 0 t, it is 0. And then you can complete the Fourier transform, and you have this one. When you have an image, you are doing the same. So you have an image. Say that this is your axis. This is where your image is. On outside, you're assuming it is 0. Yeah, then you can compute your image Fourier transform. And now it is a vector. Okay. So this thing here needs Fourier transform. Okay, so the continuous Fourier transform assumes a continuous image exists in a finite region of an infinite plane outside the image is 0. That is. Or what about the discrete Fourier transform? You may remember from 1D sequence. So in 1D sequence, you have x of n, and this goes to n minus 1, and you have here some. You may remember from 1D, so I'll go in the other direction. So I'll go in the other direction. This was called like this. Do you remember these things? That the Fourier transform of a discrete signal is a periodic signal. Now here it is continuous. So for every discrete frequency omega, you have a value. Okay, so here it is continuous, here is discrete. And then what you are assuming is that this signal is periodized. So it is the same signal that is periodic. And then this sample is here. So what we are assuming is that this signal is periodic, and then this is the Fourier transform. What is the equivalent with images? With images, you have the same concept. So you can think of this as, so instead of being periodic, I can take this signal as a tape and put it in the circle, so close the tape, and then I'm running over the samples whenever I reach the last sample, the tape, I have reached 360 degrees, and then I find the next sample again. So this is the same as saying it is periodic. So with images, we have the same. So I use some more space. So you have your image here, like this, and then you're assuming that it is periodic. It is periodic in all directions. I'm just making one copy. You have many, infinitely many copies. And all these copies are the same. Okay, and then you have the Fourier transform. So you have the Fourier transform. And the Fourier transform this omega is also periodic. So we have here kind of, this is the equivalent of the triangle, and now it is 2-dimensional. Now you have these copies. And they are separated. So the frequencies, they still go from -pi to pi. But now you have multiple copies of this. So the Fourier transform, so it is the same concept as in one dimension. In one dimension, if you have a discrete signal, you periodize it. So you have a discrete, you periodize it. And then your Fourier transform is periodic with period 2 pi. Here it is the same with period 2 pi, but now it is two-dimensional. And this you can think of it as terminating on a tail and making it periodic because you are running a circle. How to make the same concept in two dimensions? So instead of making it in a tail, you are making it in a torus. So when you make a whole turn, you are running from here to there, and then you are back to the same point. So this is what happens when you travel in this direction. And when you travel in this direction, it's the same. So you start traveling. When you reach this point, you have to go back to this point. So it is the same as if you are turning in this direction. So then the equivalent of putting it in a tail for one dimension, it is putting it in a torus for two dimensions. But I think it is more simple. It is periodization. So you take an image and you make it periodic. You take an image, you make it periodic. So the idea of the torus, some people may be useful, for me it is not so useful. So same concept as the Fourier transform. So you take your image, you multiply by your basis. Now we understand this term. This term is to make these complex bases to be unitary, so to have unit terms, and then you recover it. Okay, so now we may wonder, okay, these things here, these bases that we have in here, how do they look like? So they are complex value waves in two dimensions. It is the same as with in one dimension. So in one dimension, this is complex value, but we typically present it in this way. Say this is my wave. This is time. But actually, what I represented here is the real part of the basis, because I cannot represent the basis. I'm just representing the real part. Okay. So let's do the same, but now with images. So let's represent the real part of my complex value, of my complex value wave. Okay, so this is my complex value wave. So we have for him U and B are the frequencies. So if you take the frequencies, this is for me this is omega x, omega y. So given two frequencies, you can compute the. So this is just a vector. So you can put this vector in polar coordinates. Take this length, that will be omega, this angle that will be theta. And then it is more clear my notation. So let's say I have two frequencies, omega y, omega x. I have a point here, and then this point, that is omega x, omega y. You can also put it as in polar coordinates as omega times cosine theta, omega sine. This is and omega is just this thing. So omega is the length, C, theta is the arc, tangent is omega y divided by x. So these are the polar coordinates. These are the polar coordinates with this length and this angle. And then we can express it in whichever way. So you may use Cartesian coordinates or you may use polar coordinates. This we have the polar coordinates. Very good. So now we can, because this is a complex exponential, we can compute the cosine of the argument plus minus the I times the sine of the argument. And then we can plot what is the real part. The real part. So the real part looks like this. So now that we are plotting a cosine, what we have is a 2D wave like this. So let's see. So in this 2D wave, we have the same concepts that we have. We have an amplitude, that is the number in front. We have a period, that is the separation between two equivalent points. And this period is, before it was 1 over the frequency, we will see it now. But now we have also two things, that is the orientation of the wave. This orientation of the wave is this omega x, omega y. So this wave is propagating in this direction, the direction of omega x, omega y. And it was R and C. And then, and you see the sine of theta, the cosine of theta, that somehow involved in this propagation, maybe creating in the direction of theta. So theta has to participate in it. Okay, so what is lambda? So lambda before it was 1 over the. Okay, so lambda, we will make it later more complicated. Okay? But for the moment, let's say that the image is a square. So we have n times n squared image. So the radial frequency was 2 pi omega divided by n. This omega is the polar coordinate. So it is the length. So omega divided by n is the frequency, and then the length, the wavelength, is the inverse of this one. So it is n divided by omega. So the separation between two equivalent points is n divided by n. And then we have phase shift. So in this way that we have before, we had a wave somewhere. This one. This one. Okay, so I can plot a new one that is shifted with respect to this. So let's say it's this one. Has the same wavelength, but it is shifting. So this shift is determined by by phi, and this phase shift, that typically when you write the cosine, write cosine omega t plus phi. So this plus phi is the one that makes the wave move back and forth. So this phase can also have dimensions. So in 2 dimensions, you can also have a phase shift. And then it is whether your maximum is at the 0, 0, or you make a phase shift and then you move in the direction of the propagation by the amount given by the phase. This phase shift is a scalar. Okay? It is a single number. And it applies in the direction of the propagation. Okay, so now let's play with images. So let's say that we have this image, we compute the Fourier transform, and then the Fourier transform we can plot the real part and imaginary part. And these are the frequency axes. So this is omega x, omega y, the x omega y. This is real imaginary part. Then, yeah, we can put it in Fourier polar. And then let's make it more complicated. Before our images were square, now they will not be square anymore. So they have any number of rows and columns. So we have R and C columns. And then we can define many different frequencies. So let's see. Okay, so these U and V will be indexes. Okay, so they are the same road here, I and J. So they go from 0 to R minus 1 or C minus 1. So this I and J were arguments in the frequency, and they have the same range as the input. Okay, so this is U and V. U and V are indexes. So now we can U divided by C, V divided by R, and that is giving you two frequencies, omega x, omega y. Very good. Now, I can compute the inverse of these ones. So I will have a wavelength in x and a wavelength y. So now you have to weigh one in x, one in y. You will see y. And we have the wavelength in the direction of the wavefront. Okay, that is different. Okay, so let's see. So let's look at this. So here we have one of these waves. If you look here, just concentrate in this direction. So you see that there is a wavelength. So there is a distance between one point and the equivalent one. So this distance is the wavelength in x. This distance that is larger is the wavelength in y. And there is another wavelength that is the wavelength in the direction of propagation. That is the direct wavelength in the wavefront. Okay, so these are the three wavelengths that now we have. And it is the same as the three frequencies that we have. We have omega x, omega y, and omega. So now we have lambda x, lambda y, and lambda. So we have introduced all these things. And then we have to define the angle. So the angle is the arc tangent between omega x and omega y. So omega y divided by omega x. You know this minus 1 is arc tangent. So it is the inverse function of the tangent. Now the 1 divided by 2. Okay, good. So yeah, so we have introduced this thing. And then the Fourier coefficient. The Fourier coefficient is a complex value number. So we can compute the amplitude and phase of that number. So instead of real and imaginary parts, we can compute the amplitude of the phase. And this is all together. This is this. Yeah. So the phase of the Fourier transform, this phase phi, is the one that shifts the wavelength, the wave, to the right. Okay, so this is coming from the Fourier transform. All the other parameters, they are given by the basis. So given the basis, you know lambda x, lambda y, lambda, you know omega, you know theta. But this one This one is given by the image. It's not given by the basis. And the amplitude is given again by the image. Okay, so this is A that is coming from the Fourier transform. This is coming from the Fourier transformation. And all the rest of the parameters, they are coming from the basis. So, do you remember this drawing at the beginning? So we were saying any 1D signal can be decomposed as a sum of waves where you are controlling the amplitude, the phase, and the frequency. It's the same. So now what we are saying, any image can be decomposed. Waves where you are controlling the amplitude, the phase, and the frequency. Actually the same, exactly the same. Any image can be decomposed. So yeah, we take the image. Here we are plotting amplitude squared, and because there is a central values, they are much larger than the rest, and we are putting a logarithm because otherwise you couldn't see anything. So here is the phase. So we have shown before real and imaginary product. Now with amplitudes and phases. Real and two different representations of the same Fourier transform. Right? This same information. And power spectrum. Okay, so power spectrum is defined in this way. So let's do it in one. You have T, you have X of T, and you have any signal here, any one. Okay, let's say that this is a random process. So now this is X1. So you observe the same process again, and now you get something similar, but not exactly the same. Okay? So it is somehow similar to that, has some kind of similar properties, but it is not exactly the same. How do you define the frequency at which frequencies you have energy here? These you have from random signals. You have taken a course on random signals. So you may remember this thing. So X of T is a random process. Okay? This is realization 1, this is realization 2. So now you can compute the autocorrelation of this process. So the autocorrelation of this is the expected value of X of T. Do you remember that thing? That was the autocorrelation. And now you do the Fourier transform of this. And this is your power spectrum. Power spectrum density of X at the given frequency omega is the Fourier transform of so I'm using curly brackets when you have an operator. So this is an operator. This is an operator. Then you use curly brackets. Okay, so and these or something like this. Remember, this is omega, this is power spectrum density of L is omega has to be strictly positive, so non-negative, strictly non-negative. And in the particular case that this signal is not random, so if this signal is all the time the same, all the time, then this thing, so if X is deterministic, so it is not random. If it is deterministic, then this is the Fourier transform of omega. You may remember that. Okay, so here we have the same. The power spectrum of an image, assuming it is deterministic, is the Fourier transform of the image squared. So you take the amplitude, that is the power spectrum. That tells you how much energy you need. Any question?